evening. So at the time, we computed the one-loop amplitudes, one-loop, two-body amplitudes in QED and in GR. And we found that they have, at least the classical parts, have this general structure. There's a box integral, there's a cross-box integral. So there's a cross-box integral. And then there are some triangle integrals. I guess I drew them backwards, and this one. And then there are further pieces that are definitely quantum mechanical. They contain things like bubbles and so on. So we discarded this. We kept these things, and the plan for today is to analyze these. And at least the plan for this part of today is to analyze these amplitudes and extract the Hamiltonian and the radial action, and basically make contact with the first lecture, and the one in which we had to subtract something to construct the potential. So we're going to get the potential at order g square, or at order alpha square, and IR at that same order. So in preparation for this, yesterday we made use of this interesting observation that in the classical limit, the coefficients of the box and of the cross-box integral are equal, and they're also proportional to the coefficient of the amplitude, or rather the potential at, I guess this is C1 square. At the three-level potential. And using that, we noted, because of this equality, the box and the cross-box integral, they always come together. And there was a little bit of thought that led to the observation that the top propagator in this is the only thing that's different. So because of this equality, and because we are working as an expansion in small momentum transfer, these two guys combine and produce for us a delta function. So morally, what we get out of this box and cross box is really a box that has one line that's perpetually cut. This is a manifestation of the fact that at some point we made an argument that we want the internal lines to be close to on shell, and this is a manifestation of that. This is a realization of this. And in fact, even closer realization of that is that, strictly speaking, both lines should be close to on shell. So a tiny manipulation based on just integral changes of variables in the integral, which is this, exposed another cut, namely another cut for this line. So everything hangs together. We wanted the insides to be close to on shell, and they are close to on shell, perhaps a little too close. But of course, there are corrections to this that are hidden in the dots. As it turns out, these first corrections cancel if you integrate them out. And this is exactly related to what Donald said yesterday, that it was a similar feature there. So the correction has a square here, and that is just integrates to 0 for whatever reason. Interestingly, it integrates to 0 in 4 dimensions. It does not integrate to 0 in dimensions that are not 4. All the same, we're not going to worry about them. Right, so we're going to use both forms of this integral for different purposes. And at least for the purpose of evaluating the potential, we need to further evaluate this integral, at least one of the 4, or rather one of the D integrals. And that is usually done by evaluating the time integral using the delta function. If you go to the center of mass and crank through, this is what comes out. There is a factor of the energy, which you can see comes out of the delta function, and then the remaining propagators basically are the same, except that now they're 3-dimensional. This delta function is going to set the energy, the L0 is going to set L0 to 0. So we started with the box. Right? We started with a box with one cut line, which is this one. And if we use this delta function, it becomes a triangle. And that triangle is, this is a 1 here. This triangle looks like this. except, so this is in d dimensions, this is in d minus 1. Okay. So this is the story about this integral, and we're going to see this, we're going to use this form. Now, the one thing that's worth noticing is that this integral is in fact divergent. This is divergent, and this is important. It's not the standard UV divergence that you're used to in quantum field theory. It is, in fact, divergent in the infrared, which means in the parameter space when L vector goes to 0. Right, so there are d minus 1 or 3 L's, and then there are 2 here and 1 there, so it's d3L over L cubed. That is divergent as L goes to 0. Of course, this is finite in the UV because there this thing also fixed. Now, what does this mean? It means that the amplitude has a piece that we really don't care for. It's this one, right? And this is also the part that by counting of Q is superclassical. How do we see this? Well, this we can see easily here. This is just a box integral, nothing in the vertices, so it's a DDL over, so this is, it has Q to the 4 from the measure, and it has Q to the 2 from here, Q to the 2 from there, and 1 Q from the matter propagator, so this is 1 over Q square. Remember, what we really wanted for the classical part at this order is linear in Q. So this order we want 1 over Q, linear in 1 over Q. So this is the superclassical part, or the classically singular part. So somehow this has to go away, both because of this and also because it's divergent. So let's see how this happens. Maybe I should say it should go away from observables. Amplitudes, you know, they can do whatever they want. Amplitudes are not observables, despite what you might have heard. Okay, so before observables, there is also something else that should be finite. Anybody can guess? Right? The potential should also be finite, or the Hamiltonian should also be finite. Why? Well, one of the integrals of motion happens to be the energy, which we are in if we are in the conservative regime, it's the same as the Hamiltonian. So if this is not finite, then we have a problem. So we are going to see the cancellation of this guy when we construct V. So to construct V, we need to step back and look at our EFT action, which, if you remember, it looked like a dagger. Let me call them I, not to write the same thing 100 times. I dt minus square root of pi square, p square minus mi square, ai. And then we had a1 dagger, a2 plus, a2 dagger, a1, a2, v. And this V started out its life as a sum G to the N over R to the N, and then we had some Cn's. And if you remember, we, this is of P and of P prime. Sorry, this is P and the P prime is here. If you remember, we had a little bit of a discussion about the argument of C, right? So when we determine them from matching, it's given by one momentum, but we have to push it off shell, so that's a prescription. And the prescription was, so what does this mean? So this is the Feynman rule corresponding to this V, this is P, this is P prime. So it's the sum of the squares, half of the sum of squares of these two. Why is that? Well, the error that's being made here is of order Q, because the difference between them is of order Q. So classically, this shouldn't matter, but one really needs a prescription. And this happens to be fairly convenient. Everybody remembers this? I see one yes. Okay, I see two yeses, so I'm going to assume that everybody says yes. Right, so what do we have to do? So the amplitude, which we need to match with this, is the following, is given by two graphs, this one and this one. So this just gives us minus IV. So I'm going to ignore for a second the fact that the potential, this is V, the potential is a series. This is IV, and of course at this order we need to pick out the term that has G square only. And this is somewhat more complicated. This is an integral, and I'm going to call this momentum K, and this momentum minus K. And this is minus IV. And then there are these two propagators, which look funny. There's G of omega and K, G of omega and minus K, and then IV. And maybe I should put some arguments here. This is K and P prime, and this is K and P. So this is P, this is P prime. Okay. Any questions? So this is just Feynman diagrammatics applied to this Lagrangian, to this action. So, and there is a plus here. So what does this really mean? Here we need to pick out the term that's of order G square, and really that's the guy that we want. It's C2 sitting in there. And to have the same order in G, this is one loop. To have the same order in G here, we need to pick here order G, and here order G. So again, as you may remember from our first lecture, in non-relativistic quantum mechanics, an amplitude was given by a sum of two pieces, a piece of the potential at higher orders, and then pieces that come from products of potentials at lower orders. And this is just a realization of that. There we had a single Green's function. Here we have two. And the difference is just from the structure of the equations that we're trying to solve. All right, so and the integral is over, as of course, d omega dk over 2 pi dd minus 1k over to the d. Okay, so we need to expose this and do some of the integrals here. The thing to notice is that the potential is independent of omega, of the frequency of these gravitons. So we can carry out the omega integral for pretty much any value of this potential V. So what comes out of that is, so let's call this thing I delta. Maybe this is kind of a lousy name because it gets confusing with the delta that I put in the exponent of the action. But I'm going to skip the bar, the blackboard bold on this delta, so maybe it's okay. So I delta. This is, I'm going to define this to be integral d omega over 2 pi. And then this is I divided by omega minus square root of k square plus m1 square. And then there's another, so this is one propagator that comes out of this. And then E1 plus E2, let me call this E1, 2 plus omega, actually minus omega, minus square root of k square. Actually, this is not k square, this is, yeah, it's k square plus m2 square. Right. So we can do this integral over omega, and the result is fairly simple. This is just I divided by E1, 2. Maybe I should call this k prime. And this is k prime. So it's 1 over E1, 2 from here, minus square root of k square plus m square, minus square root of k prime square plus m square. Okay. So what do we do with this? K prime square. So k square, k prime is k minus p. yeah, so this is, we get to expand k square minus p square is of order q square. It's in fact equal to q, it's proportional to q square. So we get to expand this as follows. This is 2i u1 e2 over u1 plus e2. And then k square minus p square. So this is one of the classically singular pieces. And then we have corrections to this. Divided by 2 e1 e2, and then e1 plus e2 square plus higher orders. Okay, so now with this in hand, so this is our I delta, which is the effective propagator made up of two propagators in there. So with this in hand, we get to try to compute this and see what happens. So what happens, it's useful to restore, it's of course useful to Fourier transform these things back and think of this diagram as having these gravitons that were integrated out at tree level. And it's also useful to restore, well, to call this thing something else rather than their momenta. So this is Q minus L. And then, okay, so let's give this thing a name. This thing, let's call this VI from iteration. So VI, or maybe MI, this is the 4 pi's are here for convenience. There is a C1 p square plus k square times 2. So this is just this argument evaluated on these two momenta. And then there is a p minus k square. This is the 1 over q square from tree level. And then there is that big I delta, from which for the time being I'm going to keep just the leading term, minus twice u1 e2 over u1 plus e2, 1 over k square minus p square. And then there's another guy which looks exactly like that, except it has other momenta, c1 of a half p prime plus k square, k prime square, divided by the same p prime minus k square. And then, of course, there's the one integral that we didn't, well, 3 integrals that we didn't do. d3k over 2 pi to the 3. So, so this is an integral which looks funny. It has things in here with bizarre arguments. The integration variable is in the argument, which superficially makes it difficult to integrate. But the thing that is worth noticing is that really in here we are still interested in the classical p's. So here p plus k does have a piece that is of order q, so we can expand in that. And the same here. So let me write some momentum conservation. So p minus k, I'm going to call this L. Right, so what is p minus k? That's this picture. This is p, and this is k. So this is L. This is a momentum transfer. So L, we want to expose the things that are of order of the momentum. This is L. And then there's, of course, 1 over p prime minus k, which is on the other side, square. This is 1 over L minus q square. And then there is also 1 over k minus p, which comes from the expansion of this propagator, which is, if you work it out in these variables, happens to be 1 over 2 p dot L minus L square, or plus L square, plus L square. Okay, so with this reparametrization of the momentum integral, things start looking a little bit better. In the following sense, we have a propagator that we recognize. We have another propagator that we recognize. And yet another propagator that we recognize. Now all we have to do is mess around with the numerators and extract the pieces that we care for. So to do this, so what does that mean? We have, so let's look at these guys. So C1 for half p squared plus k squared. So if you rewrite k in terms of, so this is k. If you rewrite k in terms of L and p, what you should get is that this is approximately equal to C1 of p squared. Not surprising, k is different from p by something that's of order q, namely L. And then there's an extra piece here, which is p dot L C1 prime of p squared. Right? And of course, there are further corrections. How many corrections do we need to keep? Well, we need to keep as many as necessary to turn this from something that is super classical to classical and junk everything that doesn't do that. So what's the order of this? So this is 3 momenta in the numerator, 3 L's or 3 Q's, and in the denominator there are 2. 2 here, 2 there, and 1 there, 5. So we need to keep at most 2. I would have thought that there's at most 1. What happened here? Let's get back to that. Okay, so similarly, there is a C1, the other C1. So this is also approximately equal to C1 of p prime square plus an extra bit that's basically p dot q minus L, C1 prime of p square. Okay. What happened here? I'm a little confused. Okay, so overall, let's make a table here. The terms to keep. Right, so we have terms to keep here, which are C1 times C1. And then there's an integral, ddl, d3l, 2 pi to the d. And then there is here 1 over L square, L minus Q square, and L vector square. Oops. L vector, vector, vector. And this is, from here, there's a 2p dot L. Right. In principle, we might need to expand this as well, but guess what happens? So if we expand this, then we get p dot L squared. So if we expand this, we get L squares. L square cancels this L square. So as Donald was saying yesterday, the would-be box, perhaps with a cut line that we integrated, gets one of the vertical propagator collapses. We get a triangle. There is no Q dependence. There is no Q dependence in that. We can junk it. So we can ignore, for our purpose, this extra term here. So that's all that we need to care for. There's another term that's also proportional to C1 times C1, which we are not going to evaluate. It's important. It comes from these propagators. These ones, it's integral d3L over 2 pi to the d, 1 over L square, L minus Q square. And then there is this term here. So notice this term has no 1 over Q's in it. This is the one that we played with up to now. So that one, the first one is this. The second one just brings a factor of E1 cube plus E2 cube by something. 1 plus E2 square. So, and then there's another term, which is this guy. So it's a C1 prime times various integrals. So in here, this guy cancels that. So it survives as d3L over 2 pi to the 3. And then 1 over L vector square, L minus Q square. OK. Now, any questions? Yes, of course. Thank you. Childhood trauma. Every time I see a loop integral is in d dimensions. Right. So to correct what I said a second ago when I got confused to what order we need to expand, remember that this potential or this amplitude should behave as 1 over q, right? Because that's what we're after. So all of the terms that I wrote here are of that order, right? So 3, so this one is super classical. So this guy is the friend of ours that we need to attempt to cancel. This one is good. It's 3 divided by 4. So this is of order 1 over q. So this should be classical. And this one is the same, 3 by 4. So this is 1 over q. So it should be classical. So I'm going to spend the next minute or two trying to figure out what's the fate of this guy and in what sense it cancels the infrared divergent term that we had before. In fact, there is, when I said that I'm going to spend a minute or so, is because there is really not much time to spend. All you have to do is look at this and notice that everything in this box is the same as what we have up here. Right, so this integral here is exactly the same as the integral that we have in the box out there. The one thing that you need to care for is that the coefficients are correct, namely that these coefficients are the same as those that come out of the amplitude. Notice here we have a square of the coefficient of the 3-level potential. And this was one of the features that we saw yesterday, that these coefficients of the box and the cross box are have in fact this property. So this is V1, this guy. So now all that you need to actually do is make sure that all the pi's and the 2's and the 3's and everything else is correct. If you don't mind, I'm not going to trace factors of 2 and signs on the blackboard, but they're in my notes if you care to ask for them. Or you can also work them out yourselves, which would probably be a much better idea. Nevertheless, I'm not going to assign this as an exercise. Right, so this said, I'm going to quickly delete this so you don't ask questions about it. Incidentally, just as in previous lectures, you should feel free to interrupt and ask questions, even though it's Friday. All right. So, if you put everything together, what you find is the following expression. So by putting everything together, I really mean add up all these terms together with the one that used to be together with this. So what we find is MEFT is minus 2 pi square G square divided by Q, and this is C2. And this is the guy we're after, this C2. And then we have a lot of extra annoyances that come from elsewhere, namely from these integrals. This one, which we're going to keep as it is because it cancels. As a whole, we don't want to evaluate. And then from these things, which they are all computable. So what we find is the following. I should have written this before. G square E psi norm of Q, and then 1 minus 3 psi C1 square plus 4 psi square E square C1 prime And that's it. And then there is plus our friend, which is that guy, with coefficients included, 32 pi square g square e psi. I'm going to tell you in a second what psi is, c1 square, and then the integral, d3l, 2 pi to the 3, 1 over l square, l minus q square, 2 p dot l minus I epsilon, to be pedantic. And that's it. So this is MEFT, and psi is U1, E2 over U1 plus E2 square. So the thing to notice, there are several kinds of terms. There is the guy that we want, and then there's a piece that survives in the classical limit, but it comes from the iteration. It comes from this. And then there's an extra term that comes from the iteration that survives, this one. Now this one, perhaps, because it looks this way, it sort of looks more like a triangle than anything else. I mean, numerically, these are both triangle integrals, but this looks more like a triangle than this one. This one is more of an iteration type because it looks very much like the divergent guy. All right, so that's that. And then if we combine this with the amplitude, what you find, so if you equate MEFT equals M1 loop 4 GR. Again, this fellow cancels, so we can solve for C2. And C2 comes out to be nu square, M square. Again, there's a little bit of algebra, and there's a little bit of evaluation of the triangle integrals, which we are going to get to in a second. Over C, gamma square, so gamma is the usual Lorentz factor. And then this looks 3/4, 1 minus 5 y square, and then so this is from triangles, and then there is some extra stuff that comes out of these fellows. Minus 4 nu y, 1 minus 2y divided by, I guess this is gamma psi, and then minus nu square, 1 minus psi, and then 1 minus 2y square. Anyway, the only reason to write this for you is to show you that it exists, and to encourage you to take it and solve the classical equations of motion with it. It's not as terrible as it sounds. You can just keep it as C for most of the calculation and plug it in at the end. But the thing that I do want to emphasize yet again is that this term, as it stands, cancels against this. And that relies on this particular structure of the coefficients in the classical limit. Okay. Any questions? What's new? Yes. So new is M1, M2 by M1 plus M2 square. Okay. So again, the thing to notice here from this structure is that there is a piece that comes from the amplitude, this one. I didn't, so this is for GR. I didn't write the coefficients for GR, but C triangle is proportional to C. The other triangle is proportional to 1 minus 5y square. So y is P1, P2 by M1, M2. So this term comes straight from the triangles, and these guys, they come from these guys, from using the specific form of C1 and C1 prime. So again, what I wanted to emphasize is that it's not that in this form the Hamiltonian picks up just a piece from the amplitude, but it has also some pieces that come from the subtraction of and from the matching with the effective field theory. Okay. Any questions? Any more questions? Right. So how do we compute the triangles? Well, maybe we can see the triangles in the exercises. How about that? Okay, so there was the other strategy of extracting classical physics, which was to construct the radial action. So let's talk a little bit about that. So if you recall, we wanted to extract, so the radial action was identified like so. There's this operator, blackboard bold delta, not to be confused with that delta, in terms of which the two-particle S matrix was that, and the radial action was the expectation value of delta between P1 prime and P2 prime, or P3 and P4. But the S matrix started out its life as 1 plus I delta plus a half the other delta plus a half I delta plus and so on. So to extract this, the one loop correction to I delta, of course we need to subtract again something that is, so one loop here, order G square here. This one interferes with order G in there and order G in there. So the actual S matrix element is a combination, at one loop is a combination of this guy and that guy. So we need to separate them somehow. So the separation goes along the lines of what we discussed, I guess, on Tuesday. So we insert here a complete set of states in the form of a phase space integral. And the reason it's just a phase space integral is, one, because we assumed that, well, because this form stands only for elastic scattering, so we can't be producing anything else than two particle states in the middle. And even if we relax that, which some people are trying to do these days, at this order, as Donald described for in the KMOC form, there is nothing else you can put here. If you do put something else, then you get a two-loop piece. All right, so we throw in here a two-particle phase space integral. What might that be? Well, it's ddl1 over 2 pi to the d, ddl2 over 2 pi to the d. And then we need the phase space pieces, so those are a delta. Nominally, they should be p squared plus m squared, or minus m squared, depending on your conventions, because that's the own shell condition. But as an expansion in Q and to classical order, it's the same as 2L dot P1 and delta of 2L dot P2. And then there is, of course, maybe I should write them better. There's a delta of L square. L1 square minus M1 square. Delta of L2 square minus M2 square. So written this way, one still needs to further expand. And use momentum conservation and so on. Okay, so all in all, this should look very much like the following. ddl1, ddl2, and then here we have an IR. So this is a three-level part. Right. Okay, so if we expand this, and we remember that the radial action looked at 3, looked very much like some coefficient A1 that we computed, and then there was a Q square, right? And if we also remember, so this is Q in here. So if we remember this, and if we use momentum conservation here, this just becomes, oh yeah, there are some delta of L1 square minus M1 square, which I inconveniently forgot. So if you use this in here, then this happens to be d dl1 over 2 pi to the d, d dl2 over 2 pi to the d. And then expanding these leads to, there's some 2 pi's here. 2 pi delta of P1.L P1.L1. There's also some delta function P2.L2, and then there is delta of L1 plus L2 minus Q, and then there are the propagators in here, 1 over L1 square, L2 square, A1 times A1. Okay, so let's see, do we recognize this? Well, that guy, if you decide to solve the delta function for L1 plus L2 minus Q, that guy is the same as this guy. Right? So that one is, and again, whether the two are actually the same relies on the fact that the coefficients will in fact work out, and they do. There's a tiny difference between C and A, but that's just an overall factor. C1 is in fact proportional to A1, and if you actually keep track of the factors, then they do cancel out. And the conclusion of this tiny enterprise is that this thing, the expectation value of I delta, P1, P2, P3, P4, at one loop. This is the same as C delta, C triangle, I triangle, plus C the other triangle, I the other triangle. Okay, so what does this tell us? Well, it tells us that at least on the surface there's an enormous difference between the radial action and the Hamiltonian. I'm pointing to the wrong Hamiltonian, and the Hamiltonian. Right? There's this piece that's common. So this C delta here is proportional to 1 minus 5 y squared. There's this piece that's common, but the Hamiltonian has a lot of other stuff that comes in, whereas the radial action doesn't. So in this sense, the radial action is a lot cleaner than the Hamiltonian. Now, what is the purpose in life of these things? Well, if you think about, ideologically solving the equations of motion to second order in G, well, how do you do it? Well, you first solve to leading order in G, and then you iterate. The purpose in life of these guys is to clean up the iterations from the Hamiltonian. And this guy is morally the main origin of the order G square correction to say the scattering angle. Here, the story is a lot cleaner. The scattering angle is just minus dir by dj. Actually, this is equal. So what you see is what you get. Okay. So if you actually want an answer to this, the radial action is A2 divided by Q, and A2 is just 6 over 32 square. There's a G square here. And then some masses, M1 square, M2 square, M1 plus M2, and then 5y square minus 1. Right, so from here, the scattering angle will be proportional to just 5y square minus 1. And it will work out also from the equations of motion, just a lot more complicated. Okay, any questions, concerns? I can certainly appreciate this was fast. Yeah, having done this, I can go fast, but please feel free to ask for clarifications, though perhaps at the end of it is a little harder to go back. Okay, so, sorry? All right, so the last thing that I wanted to tell you about this is when am I supposed to stop? Later. Okay. All right, so let's go a little bit more formal and worry about exponentiation of amplitudes. So what do I mean by this? So we had this formal argument that the S matrix has to look this way. The question is, does it really look this way? And can we make an argument that, in fact, it does look this way? And that's what we're going to discuss briefly. So the argument for that is to, in fact, use something simpler than the full theory. We're going to use the EFT for this. Why are we going to use the EFT and not the full theory? Well, the EFT is simple. Right? The only thing that it knows about is that it has there is this effective interaction. So it has propagators which are a little funny, but and then it just has this interaction. So we can very compactly write amplitudes in terms of just this V. Right? And all the amplitudes look like this. Is this plus that plus the other thing. Right? So you're just in time. So we have here just a V, and V's here, and this just captures all the amplitudes, and we don't need to worry about graviton exchange and what cuts we keep and how do we evaluate integrals and so on. Everything is there. Not only that, but also this thing is in fact simple, right? We computed it, and I, of course, erased it. So this I delta, it started out its life as a product of two propagators with an integral, and we evaluate the omega, the frequency integral, or the energy integral. And then we found this, E1, E2, over twice. E1 plus E2. 1 over K, so this is K, this is P. 1 over K square minus P square plus extra terms. So this term here looked very much like 1 over twice P dot L plus L square. So it was approximately equal to the precision that we cared for. And also because this thing collapses propagators buried in here, it was 2 P dot L. And it turns out to be very convenient to change variables from this P to another P. Namely, P goes to P bar equals P bar plus or minus Q over 2. The purpose in life of this change is that, well, P dot Q is of order Q square, so we ignore it by hand by actually looking into the calculation. P bar has the nice property that P bar dot Q is exactly 0. So we don't have to worry about, oh, there is a subleading term in there, what do we do with it? So this is very much analogous to something that Donald did yesterday, or perhaps in Yeah. I think you called it P check. Anyway, you had a P that did something like this. All right, so there is this factor here which is a little bit annoying. So let me define a new variable, which I'm going to call R, which is V times this thing, which is V times that thing. Yeah, 2E1, E2 over E1 plus E2. All right. So having said this, we can write a generic term in this series, which how does it look? So the amplitude starts out its life as just R plus there's an integral dl1, dl2, and then delta of L1 plus L2 minus Q, and then there is an R, and then there's an R of L1. There's 1 over twice P bar dot L1 minus I epsilon, and somehow there's a sign which I inconveniently lost along the way, and then there's another R here of L2. So this is the thing for this graph. And then there's, of course, another one, which includes DL1, DL2, DL3, and so on. And then 3 R's. And then there's a delta of L1 plus L2 plus L3 minus Q. And then there's an R, 1 over this thing. There's another R, another one of these guys, and another R of L3. And then it goes on. There are turtles all the way down. Okay, so at this stage, it's useful to remember that there is a really cute identity, which a very simple example of which we encountered yesterday. So that really cute identity from yesterday is this one, 1 over x plus I epsilon, or minus I epsilon, plus 1 over minus x plus I epsilon, or minus I epsilon. This is 2 pi I delta of x. So there is a generalization of this. And that generalization goes as follows. Sum over delta of, there's a delta of sum of omega i's. And then there is a sum over permutations of the following. 1 over omega 1 plus I epsilon, 1 over omega 1, 2 plus I epsilon, 1 over omega 1 to n minus 1 plus I epsilon. So omega 1, 2 is omega 1 plus omega 2. Omega 1 to blah, blah, blah is the sum, omega 1 plus omega 2, blah, blah, blah. And the sum over permutations is the sum over permutations of omega 1, omega 2, and so on. So another term in here would be omega 1, omega 1, 3, and then the next term is, this is a product here. All right. So it turns out that this is equal to the same delta of sum of omega, and then there is a minus 2 pi I to the n plus 1. N plus 1, no, it's n minus 1. And then there's a product from 1 to n delta of omega I. Okay. So basically, whenever you have something like this, and you're lucky enough to have a sum over permutations, then basically all of these things are forced to be 0, provided that you have this momentum-like conservation constraint. So great, how does this help us? Well, we have sort of something very similar to this, right? We have these fellas, this, and these guys that I didn't write. And then at the generic term, there are things here. Yeah. That's correct. Yes, that's correct. Yeah. So omega 1, 2, blah, blah, blah is omega 1. So omega 2 plus blah, blah, blah. Okay. So for us, omega I is twice P bar dot Li. Right, so graphically, these guys start out their life as vertices. And there is L1 here, L2 there. Oops, it's in the blob. And so on, and this is P. So here we have P dot L1 because it's this propagator. The next guy is P dot L1 plus P dot L2. And as you keep on stringing them, you have P dot L1 plus P dot L1 plus P dot L2, P dot L1 plus P dot L2 plus P dot L3, and so on. Now, the thing that's important to notice is that these R's here, there are all of them. It's R of L1, R of L2, R of L3, and so on and so forth. So the product of R's is symmetric under permutations of L's, and this delta function is symmetric under permutations of L's. So even though this is a single term, you can invent a sum over permutations without any penalty, without needing to mess around with these R's. So this generic term, what does it look like? It looks very much like delta of sum of all the Li's minus Q, and then it's R of L1, 1 over 2P dot L1. Let me ignore the I epsilon, R of L2, P dot L1 plus L2, and so on. And then there are n of these. So this is the same as 1 over n factorial, sum over permutations of the same thing. Permutations of Li's. 2P dot L1. Okay. So where does this take us? Well, we get to use this, and that means that we get to evaluate, we get to kill these people here. Sorry. That did not come out right. We get to kill all of these, and in fact replace them with delta functions. All right, so this is 1 over n factorial product. Let me ignore the product. 2 pi delta of twice P dot Li. And then there's, of course, the delta of sum of Li minus Q. And then there's R of L1, R of Ln. Okay. So what does this sound? What does this look to you like? Well, it looks exactly what we wanted, right? So there are n guys. There is something symmetric here. Delta functions that don't exactly matter, but they make up phase space integrals. There's a 1 over n factorial. So if you look at this, all this stuff here, in fact, crucially because of the n factorial, it resums into something that has R and the exponent. So this is schematic, of course. Where, of course, the exponential has to do with an integral over the remaining pieces, very much in the same spirit as here. So there's an exponent of R. So this R is just the radial action, just as we saw here in the simple example of, this simple example, in fact, dealt with just this term. Right, so this is an argument based on just field theory perspective and the equivalence of the full theory and the effective field theory that in fact, our little story about the radial, about the S matrix related to the radial action, exponentiation, and so on and so forth, in fact, holds water. This construction, the story that I just described, doesn't assume this. This is an outcome of that. All right. Any questions? Okay, so this said, we are at the end of our little story about how to compute things. So how much more time do I have? 13, 1-3. Okay. Thank you. You're very generous. But maybe everybody else should chip in. If you want me to stop, I'll stop. Right, so anyhow, this brings us to the end of our story in which we actually compute stuff. So the rest of the 13 minutes, there will be mostly discussion about what happens if we proceed to higher loops. All right, higher loops are important for a variety of reasons. You know, one loop is just quadratic in G. If we want to talk to our PN friends, they always talk about these days 5PN, Ricardo. 5PN, 6PN, that goes all the way to G to the 5 or 6. So we need to do better than this. So let's worry about what happens when we attempt to do better than that. So higher loops. I guess at higher loops, we can't rely on a kind soul like Donald to hand us the amplitude, so we need to work. I mean, if he had them, he would keep them for himself, I'm sure of it. So at higher loops, we want to use as much as we can what we've learned, namely that we need to simplify the construction of the integrand. By which I mean that we need to focus on the relevant unitarity cuts in our construction. So as an example, at 2 loops, because for these I actually remember what they are, and we can in fact work them out on the blackboard. So we had 3 constraints. Every loop had to have 1 matter line. We don't want intersecting matter lines, and we don't want, at least if we care about potential gravitons, that we don't want gravitons or messengers that start and end on the same matter line. So with this in mind, if you pause to think about it, there are 3 unitarity cuts that you can construct. And of course, there are also their images under various relabelings. So this is one of them. This is another one. So the heavy dots stand for amplitudes, and the exposed lines are they are cut propagators. The vertical ones are messengers. The horizontal ones are matter lines. And then there's another one. There's a fun one. Okay. So to compute them, you need to use pretty much everything you've learned over the last couple of weeks. So each of these blobs, you get to use color kinematics, double copy, either in the BCJ form or in the KLT form, KL. Or in the KLT form. If you like graphs, if you like to play with graphs, then I would strongly advise to use this form, because KLT produces all sorts of poles that don't belong, as you perhaps saw if you attempted to solve the exercise that I left yesterday. So you need to take a KLT expression and massage it such that you expose poles. And yeah, so this is how we construct these things. And then, of course, these have to be merged into an integrand. And by that, I mean merged properly. which means to remove the overcount. What overcount am I talking about? Well, if you look at these two, in here you can imagine that there is a graph that looks like this. And in this one, there's a graph that looks like that. And this guy is the same. The resulting graph also appears here, so that has to be removed. It cannot appear twice. So yeah, and then there is integration to worry about. And so on. Now, of course, there is a little story about, again, what are the momenta? What region do we want these messengers to be in? Right, so yesterday we tried to argue that, well, if we keep them in the potential region, then that will bind everything. So if we're interested in conservative stuff, then all we need to care about are potential gravitons. And then another argument for it was that, well, assume for a second that we allow ourselves to include radiation gravitons. Then radiation gravitons can go on shell. They lead to energy loss. Energy loss is no time reversal invariant. It's no time reversal invariant, therefore should lead to odd powers of velocity. So there is a clean separation between the conservative part and the part that is being given by radiation. So we should restrict ourselves to this. That's great, except that as you go to even higher loop orders, things start going a little bit differently, because this argument, while still works, it doesn't work perfectly anymore for the following reason. Imagine for a second that you are at 3 loops. And you consider this particular cut at 3 loops. Oops. Okay, so you have 3 loops that you need to worry about here, and 4 gravitons. So the exposed lines are meant to be cut. So on-shell conditions here sets this graviton to be potential. Again, because this cannot be on-shell because of these 2 matter lines being on-shell. Same goes here. Now, what about here? Well, these guys, this one and this one, they are gravitons, but this on-shell condition doesn't constrain them to be anything, right? They could either be radiation or they could be potential. If they are potential, we really don't want them because they would identify these 2 points, leads to scaleless integrals and so on. Therefore, they could in principle be radiation. Now, if they are radiation, each of them generates a V odd, but there are 2 of them, so morally they generate something that's V even. Okay. So this is something that is called conservative radiation reaction. So the moral of this little story is that at sufficiently high loop orders, namely at L equals 3 and above, radiation gravitons, an even number of them, contributes to conservative physics. Now, let's see, let's reason our way to what might happen if we decide to ignore this feature, right? So remember that that potential gravitons had their momenta of the type Q, and there was here some parameter that prevents this from going on shell. So there is a parametric difference between these 2. So this is potential, and radiation. This is Q, this is Q, and there are some parameters here which are commensurate. So what would happen if we ignore these guys at this order? Well, we sort of have a little bit of an issue because, yeah, this guy is supposed to be larger than 1 to prevent this from going on shell, but how much large? What is large? What is, it's larger than 1 by how much? Is it 10 enough? Is it 100 enough? So there is an ambiguity in this split. Okay. So what happens when you have an ambiguity in a split in momenta? Well, this ambiguity will feature in your final answer, right? Therefore, if we focus just on this, we will have some free parameter which we don't know how to fix. And because of this, we will have to think hard and consider adding that to kill that parameter. So this by itself must contain some ambiguity parameter. And the cancellation of this ambiguity parameter will require us to include the extra region. Now, in dimension regularization, we have a very natural ambiguity parameter. Right? We usually refer to it as mu. Right? So the expectation here is that this mu will survive. But for mu to survive, usually in dim reg, mu appears to the power epsilon. So for mu to survive, it means that there's a 1 over epsilon that survives. So as a consequence of this little argument, potential region, we conclude that the potential region V or H is divergent. Yeah, is generically divergent. There are, of course, cases when it's not, such as in QED, but never mind that. So generically, one would expect that the potential region potential is, in fact, divergent. And to make sense of it, there is no way around including these other guys. I think my 13 minutes have been up a few minutes ago, so let me stop here and continue my blabbing after lunch. Thank you.
Any questions, guys? Or further questions or comments or anything else?
Yeah.
Does this have to do with the IR divergences or no,
yeah, it will have to do with some IR. So this divergence here, you can think of this as, I don't know, renormalization, almost like renormalization group or like an effective field theory, if you wish. Right? There is a cutoff here. If you look from above, this there will be an IR divergence. If you look from below, there will be a UV divergence. And if you look over the whole scale, this IR cancels this UV at this scale. So it's exactly this mechanism. Yeah.
So another thing I was thinking was that at the beginning we were talking about vanishing integrals only on 4 dimensions.
Yes.
In my head, I instantly thought about dimensional regularization, but then I actually happened to think that it doesn't matter because it's vanishing, and at the end we want to make, I mean, given the given natures is kind enough, and then and when we set D to 4, we could assume that those vanishing integrals will vanish.
Well, I mean, if they're proportional to D minus 4, then they will vanish. But yeah, I mean, there is one thing that I haven't emphasized, and perhaps I should have. This story about splitting momentum region into potential and radiation and whatnot, it's something that works great, but it works great in dimension regularization. If you decide to change that regularization, then all hell breaks loose. And in fact, the split doesn't really work. Here, one would just need to consider everything. There is no split to be had. And perhaps in the big scheme of things, this might in fact be better, because one would never encounter this divergence. but all the same, it's when you're using anything that I said, you need to write with big letters. I'm in dimreg. If I'm not in dimreg, I'm toast.
But like if the integral is vanishing in 4 dimensions, then it must be proportional to d minus 4 in some way.
In dimreg, yeah.
Yes, exactly.
Yeah,
in
yeah.
dimreg.
Yeah, I
Yes,
mean,
yes.
in fact, that integral would not be 0 if you were to regularize it with a cutoff, for example.
Oh yeah, of course, of course. Then actually this also maybe answers a question I posed to Professor O'Donnell about when he was talking about the Veltman reduction and vanishing integrals.
Passerino-Veltman.
And then I was asking about what if we
Yeah,
have
the
more
mu
dimensions?
term question.
Yeah, okay.
Mm-hmm.
Okay, thank you.
Okay, so let's thank Radu again for his lecture.